All right, welcome to the section on data transformation. In this section, we're going to talk about how to transform your data for flow-cytoscript. Transformation is really important for getting good results with high parameter data analysis, but it's unfortunately time-consuming and easy to get wrong. The good news is you don't need to do this for flow-cytoscript. Flow-cytoscript will automatically identify which cytometer you're using and apply a bi-exponential transformation that's appropriate for data generated on that machine. Currently, we have incorporated automated transformations for data from the Aurora, the ID 7000 from Sony, and BD analyzers. Now, if you're using something else like a S8 Discover, a Bigfoot, an Attune, a Z85, send us an FCS file and we'll add it to the script. Now, if you're an expert and you want to transform your data in a specific way, well, we support that. In this section, we'll go over how to do that in FlowJo and how to export your data with that transformation applied for use in the flow-cytoscript. For this, I'm using some data from a mixed bone marrow chimera generated in mice. I've gated on viable T cells here, and we're going to look at how to set the transformation for a few parameters. This is Aurora data, which often isn't displayed correctly by default in FlowJo, and that's true for many cytometers, actually. So the values on the Aurora, for example, are coded up to 5 times 10 to the 6, which is what I'm showing here, rather than about 2 times 10 to the 5. Which would be cutting off the edge of this, and that's the default based on BD machines. To change how the data are displayed, we click on this big T here next to the axis label. We get the options to customize the axis. When we bring that up, we get a histogram displaying the values for that parameter. If we want to change all of the parameters at once, we could select them in this menu down on the side here, like this. Right now, we're just going to look at one. Selecting all of them is useful if they're all displayed incorrectly because it's not set for your type of machine. Now, with the transformation, we can change several things. Starting under scale, we could switch from bi-exponential transformation to several of the types. Bi-exponential is generally quite good, so I stick with that. The other thing we can change is the max over here, which is that range that I'm talking about. So if your data are going off scale because the max is set too low, you can increase it by typing in a larger number. So for instance, 600,000, 6 million in my case. And then I hit enter for it to take, or I can change it by playing with the plus and minus signs here. Now, if the data aren't reaching the edge, you can increase how much space they take up on the plot by decreasing this max. So that data that are spread across a larger range on the axis, taking up more of the space without having any white space, that's going to contribute more to driving separation in the t-SNE and the clustering. If those data are really compressed down into nothing, well, they're kind of going to get ignored in your data analysis. So one thing that you can really take advantage of while transforming manually is that you can effectively normalize the influence of each channel on the high parameter analysis by setting the appearances to be sort of similar. The best way of doing this, of course, is in the panel design stage where you equilibrate the signal strength of your different markers by using dim fluorophores for highly expressed markers and bright fluorophores for low expression ones. But that doesn't always work out, so you can do some stuff post hoc in FlowJo or FCS Express if you're using FCS Express. The other aspects that we can look at for the bi-exponential transform are down here in this transforms menu. You can add more space below 0 with the extra log, negative log decades slider or typing in. However, if you need to do this, it almost always indicates that there's a problem in the compensation or on mixing or autofluorescence, so I would check that first. In this case, we don't need to do this because the data aren't going down there. The width basis controls the compression of the negative. Less compression, wider spread in the negative. More compression, less spread in the negative. The larger your panel, and the more spread there is in the negative, the larger this is going to need to be. For large panels in the Aurora, you probably want it between, say, 200 and 1,000. In this case, we're using BUV395, which is a channel that receives very little interference from anything else. So we can actually go quite a bit lower than that, even though this is 40 color something Aurora data. As a rule of thumb, you might want the negative, that's this peak here, to be taking up less or equal amount of space in the plot to the positives. If you have the negative separating and bifurcating like this, that's going to be treated as different populations in your data analysis, and you will get an artifactual separation of the two negative halves. So you want that negative to be one peak. So something like this might be fine, or even if you wanted it compressed more, you could do something like this, but then your positive is really compressed as well. Personally, I would pick something around there. If your marker expression is very low in a clean channel, you want to lower this and decrease the max range to make that marker show better, which is what I've done here. So I've made this smaller and I've made the maximum range smaller. We don't want to decrease the maximum range to the extent that it's clipping our marker, because then those values are recorded as a maximum value and there's no separation between them, and that will cause artifacts in your analysis. The positive log decades control over here is the final control. You can also use this to control the compression of the negative. So we can have a look at that. So you can see you can compress it more or less. In general, if you need to use this, you probably have a panel design or unmixing error, or you're working with something more than 50 colors. So I tend to avoid using that one unless it's really necessary. Once you have the channels looking the way you want, you click Save and Apply, and you can see now our dot plot has updated and our data, we can now really see that CD103, that there's a low population and a high population, and there's a difference in expression values over here on the Ly6C. And we couldn't really see that before when we didn't have the transformation applied correctly. So then we would just go through and repeat that for each of the channels, which, like I said, can be time consuming when you're working with this many parameters. After you're done, what you'd want to do is export the data. And this time, what we would do is go through the export and change from FCS3 to CSV channel values. If you export with CSV channel values, that will encode this transformation, whatever type of transformation you have applied, and the data will be exported in a CSV, which is a spreadsheet-like document where the data are now exported in a range from something like 1 to 2,000 rather than the negative 20,000 to 5 times 10 to the 6 that they are in the original flow data. All right, so that's how you go about exporting your data in the CSV format, which will save your data transformation for application in the flow cytoscript. And that's all for this section.